Two sets may share some elements. We indicate the elements in common to both sets using the overlap of two circles in what's known as a Venn diagram. The union and the intersection are two ways of combining the elements in two sets into a new set. The union of two sets A and B is the set containing all of the elements in A as well as all of the elements in B. We write this formally as A union B, where the large U shape symbolizes the union, is the set X such that X is in A or X is in B. The word OR is the most important bit here. This is like taking all of the elements indicated in this shaded area of the Venn diagram, and notice that it includes elements in both A and B. The intersection of the sets A and B is a set containing elements that are in both A and B. The intersection of A and B, or A intersect B for short, is symbolized with an upside down union symbol and is formally defined as X such that X is in A and X is in B, the word AND being the most important bit. If the elements of the intersection must be in both A and B, then we're talking about the overlapping part of the Venn diagram. Let A be the set containing 0 and 1, and B be the set containing 1, 2 and 3. What is the union of A and B? And what is the intersection of A and B? The union of A and B contains all the elements in A, so 0 and 1, as well as everything in B, which is 1, 2 and 3. So altogether, and ignoring the repeating 1, we have the union of A and B is a set containing 0, 1, 2 and 3. Remember, just to be clear, we get a set containing 0, 1, 2 and 3 from taking the union, not just the elements 0, 1, 2 and 3. The intersection of A and B will contain only elements in both A and B. In this case, only 1 is common to both A and B, and so the intersection of A and B is the set containing 1. Let's do a second example. Let A be the set of little a in the natural numbers, such that little a is odd, the odd numbers for short, and B be the set of even natural numbers. What is A union B, and what is A intersect B? The union of A and B will be a set that contains all the odd numbers and all the even numbers, which is the set of all natural numbers. The intersection of A and B would contain only numbers that are both odd and even. There aren't any numbers which fit this criterion, and so the intersection of A and B is just the empty set. Let's look at some properties of the union. Firstly, the union of any set A with the empty set is just A, since the empty set has no elements. We have a similar situation with taking the union of any set A with itself, which just gives A. If A is a subset of B, then the union of A and B is just B, because all of the elements in A are already in B, and so we don't add anything new to the union. Another example is that the union of A and B is the same thing as taking the union of B with A. The final property of unions is if we have three sets, A, B and C, we can exchange the order we take the union by moving the brackets, and we'll still get the same outcome. On the left hand side, we take the union of B with C first, and then take the union with A. We end with all the elements in A, as well as all those in B and C. Taking the right hand side, we start with the union of A and B, and then take the union of that with C. And just as before, we get all the elements from all three sets. This rule actually generalizes to any number of sets, and you can take the union in any order you like. Some properties of the intersection now. Remember, this is all the elements common to both sets. Firstly, for any set A, the intersection of A with the empty set is just the empty set. Since the empty set has no elements, it can't have any elements in common with any other set. The intersection of any set with itself is just itself. If you remember, this is exactly the same as with unions. If A is a subset of B, then the intersection of A and B is just A, the small set of the two, as indicated by the shaded area. This is because the elements in A are also in B, and just like with the union, A intersect B is the same as B intersect A. That is, the order of the sets doesn't make any difference to the intersection. Again, like with the union, the fact that the order doesn't matter extends to 3 or more sets with brackets. We can see that B intersects C, then the intersection of the result of that with A is the same as taking the intersection of A and B and then the intersection of that with C. In both cases, we end up with a set containing the elements found in A and B and C, the shaded area in the middle. Let's look at the cardinality of the union and intersection of two sets because there's a useful identity. Let A be the set containing 1, 2 and 3 and B be the set containing 3 and 4. We can see that A contains 3 elements and B contains 2 elements, and the union of A and B would contain 1, 2, 3 and 4 and so has a cardinality of 4. The intersection of A and B contains only 3 and so has a cardinality of 1. Now notice that the 2 on the left added together equals the 2 on the right. This isn't coincident, but it's always true. The identity is usually written as the cardinality of the union of A and B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. Also, because we're taking away the cardinality of A intersects B, we can also write this as an inequality. A union B is less than or equal to the cardinality of A plus the cardinality of B. We also have a couple of identities involving both unions and intersections. For 3 sets A, B and C, taking the union of A with the intersection of B and C is the same as if we take the union of A and B and the union of A and C separately and then taking the intersection. This looks a lot like multiplying out the brackets, and so it's relatively easy to remember. But how do you remember which order the union and intersection signs come in? Luckily, you don't need to. This is because the identity works if we exchange the unions for intersections and the intersections for unions. Here, the intersection of A with the union of B and C is the same as the union of A intersects B with A intersects C. As we've already discussed, these identities are similar to multiplying out the brackets, and this kind of property in general is known as distributivity, or the distributive property. You might be thinking at this point, how are these identities useful? So I'm what they call a fair weather cyclist. I only cycle in the summer or in the winter when it's warmer than 20 degrees Celsius. Let's make sets of these potential days I could ride a bike. We have summer, winter, and those that are more than 20 degrees C. The shaded area is therefore the days that I can cycle. And we could write this as the union of summer and the intersection of winter with days warmer than 20 degrees. We can use the distributive property we've just seen to work with the logic of a given statement. So if we have the set of days in the summer or winter and more than 20 degrees, the identity says that this must be the same as summer or winter and summer or more than 20 degrees, which at first sight doesn't seem to make much sense, but notice that summer or winter is any time, and summer or more than 20 degrees is the days when I cycle. We're ignoring other seasons in this example. And we're taking the intersection of these. So we get to something like, I cycle any day of the year, but only when it's summer or more than 20 degrees, which actually makes sense and is another way of saying the original statement. But what makes this more satisfying is that we've come to it from a set theoretic identity, which shows how we might use set theory to manipulate logical statements. Now consider the statement, I only wear white or blue shirts. Here we have 3 sets, shirts, blue clothes and white clothes. And for specifically blue and white shirts, we take the intersection of the union of blue and white clothes with shirts. And so the formula might look something like this. Like before, we can use the distributive rule to play around with the logic. So shirts and blue or white becomes blue shirts or white shirts. This can now be interpreted as I only wear blue shirts or white shirts. It doesn't feel too different to the original statement, but again, it's quite satisfying that it comes straight out of the set theoretic rules. But before we move on from unions and intersections, I want to show you how we can mathematically prove a statement such as this one. Remember how earlier we showed that if A is a subset of B and if B is a subset of A, then A is equal to B? Well, here we can use that exact method to prove this equation. We'll show first that A union B intersect C is a subset of A union B intersect with A union C, and that A union B intersected with A union C is a subset of A union B intersect C, which implies they're equal to one another. First, suppose we have an element X which is in A union B intersect C. Well, it's either in A or it's in B intersect C, which would mean it's in both B and C. In either case, X is in both A union B and A union C, because if it's in A, this is true, and if it's in B, it's also in C, so it's still true. So this means that A union B intersect C, the thing we started with, is a subset of A union B intersected with A union C, since we've shown any element of the left-hand side is an element of the right-hand side. Now suppose X is in A union B intersect with A union C. This means that X is in both A union B and A union C. If X is not in A, then it must be in both B and C. So it must be in the intersection of B and C, and otherwise X is in A. So X is in the union of A and B intersect C, which means A union B intersect A union C is a subset of A union B intersect C. Altogether, we've shown that A union B intersect C is a subset of A union B intersect with A union C, and that A union B intersect with A union C is a subset of A union B intersect C, which proves they're equal.